Right, so the next term in the Van Deemter equation is what we call the longitudinal diffusion term. This is represented by a B in the equation. So term B, longitudinal diffusion. So what do we mean by diffusion? Now, diffusion is just migration from an area of high concentration to an area of low concentration. Okay, and so if we're looking at a column here, I just draw my column here, and I have a band of analytes here that's more concentrated in the center than it is as you move your way out from it. Okay, as this band sits, even just not even considering it moving down the column, we're just ignoring that it's moving via the mobile phase, okay? But just in a given amount of time that these analytes are going to spend in the column, there's going to be diffusion. And so what does diffusion do to this concentration? So this diffusion is going to mean that these analytes are moving outward from the highly concentrated center to the exterior edges that are less concentrated, right? Moving from an area of high concentration to low concentration. So if I were to kind of plot a concentration profile here, so we're getting kind of increased concentration here along the x-axis, and we're just kind of looking at the spatial profile as we go down the column. We have very little, very little, very little, and then we start to get more, and we get the maximum concentration somewhere around there, and then we get it evening out. But as this is sitting, and what diffusion is doing is spreading this wider, so what you get is the center being less concentrated and the edges being more concentrated. And you might get a profile that looks something like that, okay? So over time, we haven't changed how many molecules we have present of the analyte. What we simply changed is their spatial distribution, where now we have fewer in the center at that point of highest concentration and more leading to in these exterior edges as this band sits and diffusion happens, and the band is going to broaden outward. Okay, so that's the premise of term B, the longitudinal diffusion. Now, what happens if we are moving faster down the column? What happens if now we consider the fact that we are moving in a mobile phase and this is kind of moving down the column? What happens if we run at a faster mobile phase? So we call that flow rate. So we denote that as a mu, the Greek letter mu, and that's going to be our flow rate of the mobile phase. And so what happens if we increase mu? Well, as we increase mu and we're moving this faster through the column, it's going to take less time to get through the column, right? So ultimately, going faster through the column means we have less time for diffusion to occur. So this overall effect, or the relationship between our B term and the flow rate, is inversely proportional. A faster flow rate means a lower overall B term, and a higher flow rate means a slower flow rate is going to mean more longitudinal diffusion can occur in that time, and so we get a higher overall B term. So in the Van Deemter equation, we would write this term with an inverse relationship to the flow rate, mu. Now, the other area that we want to consider is what else affects this longitudinal diffusion term. Now, if we're dealing with diffusion, we want to consider how our diffusion coefficient is, or what is the rate at which this diffusion occurs. Because there are some analytes that will diffuse faster than others. Their diffusion rates are simply faster. Smaller molecules are going to diffuse faster than larger molecules. So when we are thinking about what does this B term equal, we can write this as a relationship between a constant that's specific to the analyte and the column, and then the diffusion in the mobile phase. Okay, it's a diffusion coefficient for the mobile phase. I'll write that word, coefficient. And then this is, again, inversely proportional to mu. Okay, so when we're looking at this, the size of the particles doesn't matter, like we saw did matter with the A term, but what does matter here is the diffusion coefficient for the analyte in the mobile phase. Now, would this diffusion coefficient be higher or lower in the gas phase versus the liquid phase? Well, if we think about diffusion of gases versus diffusion in liquids, diffusion in gases themselves, the molecules are more free to move around. They are more energetic in their movements, and so that movement is, that diffusion rate is much higher in gases than in liquid. So if you're considering which term has a big effect, if your mobile phase is a gas phase, then this B term is going to be really important, and we're going to want to work at a much higher flow rate to minimize the effect of this term on the overall separation. Okay, so again, this is your B term longitudinal diffusion. That's all about how fast does the analyte diffuse outward from its nice center concentrated band, because it's diffusing from an area of high concentration to low concentration.